Welcome. Today, we're diving into the fascinating world of reinforcement learning, often called RL. Imagine teaching a dog new tricks by rewarding it for good behavior. That's the core idea behind RL. An agent learns by interacting with its environment and receiving feedback in the form of rewards or penalties. This approach is widely used in artificial intelligence, robotics, and even game development. In this video, we'll start from the basics and gradually move to real-world examples, ensuring you understand each step along the way. Let's begin by exploring the fundamental concepts that make reinforcement learning unique. Truly understand reinforcement learning, it's important to know its main components. At the heart of RL are the agent, environment, actions, states, and rewards. The agent is the learner or decision maker, while the environment is everything the agent interacts with. Actions are the choices the agent can make, states represent the current situation, and rewards are the feedback signals. These elements work together in a loop. The agent observes the state, takes an action, receives a reward, and moves to a new state. This cycle continues, allowing the agent to learn from experience. Let's visualize how the RL process works in practice. The agent starts in a certain state within the environment. It selects an action based on its current knowledge or policy. The environment then responds, providing a new state and a reward. The agent uses this feedback to update its strategy, aiming to maximize future rewards. This loop of observe, act, and learn is repeated many times, gradually improving the agent's performance. Over time, the agent discovers which actions lead to the best outcomes. Key concept in reinforcement learning is the policy. The policy is essentially the agent's strategy for choosing actions in different states. It can be as simple as a set of rules or as complex as a deep neural network. The goal of RL is to find the optimal policy that maximizes the total reward over time. As the agent interacts with the environment, it updates its policy based on the rewards it receives, gradually improving its decision-making process. Rewards are the driving force behind reinforcement learning. They tell the agent how well it's doing after each action. A positive reward encourages the agent to repeat the action, while a negative reward discourages it. The agent's objective is to maximize the cumulative reward over time, not just immediate gains. This long-term perspective is what makes RL powerful for solving complex problems where the best actions may not have immediate benefits. Another important idea in RL is the value function. This function estimates how good it is for the agent to be in a certain state or to perform a certain action in a state. The value function helps the agent predict future rewards and make better decisions. By learning accurate value functions, the agent can evaluate the long-term benefits of its actions, not just the immediate rewards. Classic challenge in reinforcement learning is balancing exploration and exploitation. Exploration means trying new actions to discover their effects, while exploitation means using known actions that yield high rewards. If the agent only exploits, it might miss out on better strategies. If it only explores, it may never settle on a good policy. Successful RL algorithms find a balance, exploring enough to learn, but exploiting enough to maximize rewards. Reinforcement learning problems come in various forms. Some are episodic, where the agent's experience is divided into episodes, like playing a game. Others are continuous, with no clear endpoint, such as controlling a robot. Understanding the type of problem helps in designing the right RL algorithm and setting appropriate goals for the agent. Most RL problems are modeled as Markov Decision Processes, or MDPs. An MDP provides a mathematical framework for modeling decision-making, where outcomes are partly random and partly under the agent's control. It consists of states, actions, rewards, and transition probabilities. Understanding MDPs is crucial for grasping how RL algorithms work under the hood. Let's look at a simple example, grid world. Imagine a small grid where an agent moves up, down, left, or right to reach a goal. Each move gives a reward or penalty, depending on the outcome. The agent learns which path leads to the highest total reward. Grid world is a classic RL example because it's easy to visualize and demonstrates key RL concepts in action. In grid world, the agent starts at a random position and interacts with the environment by choosing actions. Each action changes the agent's state and results in a reward. Over many episodes, the agent learns which actions are best in each state. This process of trial and error is at the heart of reinforcement learning. One of the most popular RL algorithms is Q-learning. Q-learning helps the agent learn the value of taking a certain action in a given state, known as the Q-value. The agent updates its Q-values based on the rewards it receives, gradually building a table of the best actions for each state. Q-learning is powerful because it doesn't require a model of the environment. See how Q-learning works in our grid world example. The agent starts with all Q-values set to 0. As it explores the grid, it updates its Q-values based on the rewards it receives for each action. Over time, the agent's Q-table reflects the best actions to take from each state, allowing it to find the shortest path to the goal. Core of Q-learning is its update formula. After taking an action and receiving a reward, the agent updates its Q value using the formula QS equals QS, a plus alpha, reward plus gamma max QS, a QS, a. Here, alpha is the learning rate, and gamma is the discount factor. This formula helps the agent balance immediate and future rewards. Two important parameters in Q learning are the learning rate alpha and the discount factor gamma. The learning rate controls how much new information overrides old information. The discount factor determines how much the agent values future rewards compared to immediate ones. Tuning these parameters is crucial for effective learning. To ensure the agent explores the environment, RL algorithms often use strategies like epsilon greedy. With epsilon greedy, the agent chooses a random action with probability epsilon and the best-known action otherwise. This encourages exploration early on and more exploitation as learning progresses. Let's apply RL to a classic game, Tic-Tac-Toe. Here, the agent learns to play by playing thousands of games against itself or an opponent. It updates its strategy based on wins, losses, and draws, gradually improving its gameplay. This example shows how RL can be used for game AI. Policy iteration is another RL method. It involves two steps: policy evaluation and policy improvement. The agent first evaluates its current policy by estimating value functions, then improves the policy by choosing better actions. This process repeats until the policy converges to the optimal one. Value iteration is a related technique that focuses on updating value functions directly. The agent repeatedly updates the value of each state based on possible actions and their expected rewards. Once the values stabilize, the agent can derive the optimal policy from them. When environments are too complex for simple tables, deep reinforcement learning comes into play. Here, neural networks are used to approximate value functions or policies. This allows RL to tackle problems with large or continuous state spaces, such as video games or robotics. Famous application of deep RL is playing Atari games. Agents use deep neural networks to process raw pixel data and learn to play games like Breakout or Pong. Over time, the agent surpasses human-level performance by learning directly from experience. Experience replay is a technique used in deep RL to improve learning efficiency. The agent stores past experiences in a memory buffer and samples random batches for training. This breaks the correlation between consecutive experiences and leads to more stable learning. Target networks are another innovation in deep RL. They provide stable targets for learning by updating more slowly than the main network. This helps prevent oscillations and divergence during training, making deep RL algorithms more robust. Reward shaping involves modifying the reward signal to make learning easier or faster. By providing additional feedback, the agent can learn more efficiently. However, care must be taken to avoid unintended behaviors caused by poorly designed rewards. In some scenarios, multiple agents interact within the same environment. Multi-agent reinforcement learning studies how agents learn to cooperate or compete. This adds complexity, as each agent's actions can affect the others, leading to dynamic and interesting behaviors. Real-world application of RL is in self-driving cars. Here, the agent learns to navigate roads, avoid obstacles, and follow traffic rules by receiving rewards for safe driving and penalties for mistakes. RL enables the car to adapt to complex, changing environments. Some RL problems involve continuous action spaces, where actions aren't just discrete choices but can take any value within a range. Examples include controlling the speed of a car or the angle of a robotic arm. Specialized algorithms like Deep Deterministic Policy Gradient (DDPG) are used for these cases. Policy gradient methods are a class of RL algorithms that directly optimize the policy. Instead of learning value functions, they adjust the policy parameters to maximize expected rewards. These methods are especially useful for problems with large or continuous action spaces. Actor-critic algorithms combine value-based and policy-based approaches. The actor updates the policy, while the critic evaluates the actions by estimating value functions. This synergy allows for more efficient and stable learning, especially in complex environments. Robotics, RL is used to teach robots tasks like walking, grasping objects, or balancing. The robot receives rewards for successful actions and penalties for failures. Over time, it learns to perform tasks efficiently, adapting to new situations and environments. Transfer learning allows an agent to apply knowledge gained in one task to a new, related task. This can speed up learning and improve performance, especially when the new task shares similarities with the previous one. Transfer learning is a growing area in RL research. Inverse reinforcement learning flips the usual RL process. Instead of learning a policy from rewards, the agent observes expert behavior and infers the underlying reward function. This is useful for tasks where it's hard to specify rewards but easy to demonstrate desired behavior. Imitation learning is closely related to inverse RL. Here, the agent learns to mimic expert actions directly without explicitly inferring the reward function. This approach is widely used in robotics and autonomous driving, where expert demonstrations are available. Despite its power, reinforcement learning faces several challenges. These include sparse rewards, where feedback is infrequent, high-dimensional state spaces, which make learning slow, and safety concerns, especially in real-world applications. Researchers are actively working to address these issues. Sample efficiency refers to how quickly an RL agent can learn from limited data. In many real-world problems, collecting data is expensive or time-consuming. Improving sample efficiency is a major focus in RL research, with techniques like model-based RL and transfer learning offering promising solutions. Model-based reinforcement learning involves building a model of the environment, which the agent uses to plan and simulate outcomes. This can greatly improve sample efficiency, as the agent can learn from imagined experiences as well as real ones. However, building accurate models can be challenging. Safety is a critical concern in reinforcement learning, especially for applications like healthcare or autonomous vehicles. Ensuring the agent doesn't take dangerous actions or learn harmful behaviors is an active area of research. Techniques like safe exploration and reward constraints are being developed to address these issues. As RL systems become more powerful, ethical considerations become increasingly important. Questions arise about fairness, accountability, and transparency. Ensuring RL agents act in ways that align with human values is a major challenge for the field. Reinforcement learning is being applied in healthcare to optimize treatment plans, personalize medicine, and manage resources. Agents learn to make decisions that improve patient outcomes using data from electronic health records and clinical trials. In finance, RL is used for portfolio management, trading strategies, and risk assessment. Agents learn to make investment decisions by maximizing returns and minimizing risks, adapting to changing market conditions. Recommendation systems, like those used by streaming services or online stores, use RL to personalize suggestions. The agent learns user preferences over time, improving recommendations and increasing user engagement. Game AI is a popular application of RL. Agents learn to play complex games, from chess to real-time strategy games, often surpassing human experts. RL enables adaptive, challenging opponents and dynamic gameplay experiences. Future of reinforcement learning is bright, with ongoing research pushing the boundaries of what's possible. Advances in algorithms, computing power, and data availability are enabling RL to tackle ever more complex problems. As RL continues to evolve, we can expect to see even more impressive applications across industries. Let's recap what we've learned. Reinforcement learning is a powerful framework for teaching agents to make decisions through trial and error. We covered its main components, popular algorithms like Q-learning, and real-world applications. We also discussed challenges and the exciting future of RL. With a solid understanding of these concepts, you're well equipped to explore RL further. If you're interested in diving deeper, consider exploring RL libraries like OpenAI Gym or reading foundational papers. Experimenting with simple environments and gradually tackling more complex problems is a great way to build your skills. Reinforcement learning is a vast and rewarding field, and your journey is just beginning.